नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार शेट्टी, फैकल्टी ऑफ सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन। मैं आप सब लोग को यहाँ स्वागत कर रहा हूं। आज हम यहाँ डिस्कस करेंगे फ्लो चैप्टर के ऊपर। हमारा वन शॉट लेक्चर है। लास्ट क्लास में हम टेम्परेचर तक पढ़ चुका है। अभी हम फ्लो चैप्टर शुरुआत करेंगे। ओके, सो फ्लो चैप्टर में क्या क्या टॉपिक्स है? वन ऑफ द इंपॉर्टेंट टॉपिक्स फ्लो चैप्टर। ओके, सो इफ यू सी the flow chapter, the flow is having certain units. Okay, the units are called as flow rate. Okay, so what are the flow rate units? So if you see the flow rate units, there are different types of flow rate units: average flow rate, mass flow rate, and volumetric flow rate. So these are the different versions of the units. See, not only with respect to gate point of view, but also with respect to other competitive exams point of view or other क्या बोल सकते हैं उसको, इंटरव्यू पॉइंट ऑफ व्यू। ओके, सो दिस टॉपिक इज वेरी वेरी इंपॉर्टेंट। सो जो लोग अगर आपने गेट के साथ साथ इंटरव्यू के लिए प्रिपेयर हो रहा है इंस्ट्रूमेंटेशन के कोर्स साइड से, सो ये टॉपिक बहुत इंपॉर्टेंट है। ओके, सो प्लीज मेंटेन, अच्छा नोट्स मेंटेन कर लीजिए। सो वहां से हम डिस्कस करेंगे। सो जितने लोग लाइव में हैं मुझे एक बार वॉइस कंफर्मेशन कर दीजिए। जो लोग लाइव में हैं मुझे एक बार गुड मॉर्निंग बताइए। अगर लाइव में है तो प्लीज कंफर्म मी। ओके, प्लीज कंफर्म मी दिस। Anybody is there in the live? Happy Christmas. चलो, if you see the average flow rate, so average flow rate का units आएगा distance per time, so that is equal to mass per time, mass per second. mass flow rate का unit आएगा mass rate, that is m dot, mass per time kg per second. volumetric flow rate का units आएगा how much volume is traveling per time, so that is q by t, so that is meter cube per second. So 1 meter cube per second is equal to how much? 10 to the power of 3 liters per second. So 1 meter cube per second is equal to how much? 10 to the power of 3 liters per second. So this quantity rate, I can write it as area into velocity. Q is equal to area into velocity. Okay, Q is equal to area into velocity. So now let us take this conduit. So what is conduit? Conduit is defined as shape of velocity profile. Shape of velocity profile of the fluid. Shape of velocity profile of fluid within the pipe. Within pipe or closed channel. Okay, so conduit means it is not the outward flow, it is an inside flow. In a pipeline, when the liquid is traveling, अगर liquid जा रहे हैं ना, इसके inside में कैसा आपको shape दिखाएगा, उसको हम बोलते हैं conduit. So see here, inside is cylindrical. Now if you take a venturi type structure, अगर venturi type structure देखो तो inside the fluid structure is like this. So from the outside it may look like cylindrical, but inside it looks like this. So this is a converging zone. This is what we call as inlet zone. This is what we call as converging zone. This converging zone. So इसको हम क्या बोलते हैं? Converging zone बोलते हैं. Okay. Next comes, this is tunnel or obstruction. Then this is what we call as diverging zone. Okay, this is what we call as diverging zone. So these are the major things. That means in a conduit the appearance will be cylindrical from the outside, but if you see inside it will be having like this. Okay, so please just confirm me. जितने लोग लाइव में देख रहे हैं, 5 मेंबर्स देख रहे हैं लाइव में सेशन को, एक बार मुझे कंफर्मेशन कर दीजिए. 5 members are watching live in the session. Okay, 5 members are watching the session. एक बार मुझे कंफर्मेशन कर दीजिए. कोई ना कोई लाइव में देख रहे हैं, मुझे एक बार कंफर्मेशन कर दीजिए बेटा. या Noted? Chalo. So this is the situation of the conduit. So conduit is having the inlet zone, there is a converging zone, there is obstruction zone, there is a diverging zone, there is outlet zone. Now this is a laminar flow. You see the laminar flow. In the laminar flow, the fluid which is traveling at the walls will be having the less velocity, and the fluid which is traveling at the walls will be having less velocity, but the fluid which is traveling at the center will be having the high velocity. So this is what we call as disciplined velocity profile. What we call this as disciplined velocity profile. Okay, so there is a defined velocities layer to layer. Okay, so velocities of the layers are predictable. So that type of fluid को हम बोलते हैं laminar flow बोलते हैं. ओके, सो लैमिनर फ्लो में हम प्रेडिक्ट कर सकते हैं कहाँ आपको फ्लूइड फ्लो कम है, कहाँ आपको फ्लूइड फ्लो ज़्यादा है, सेंटर में कैसे रहता है, हम पूरा चेक कर सकते हैं. सो नेक्स्ट कम्स दी टर्बुलेंट फ्लो. इन टर्बुलेंट फ्लो देयर इज नो discipline from top to bottom, there is no discipline, indisciplined velocity profile like this. So that means when you are pressing that pipe or when a disturbance is created in that particular pipe, definitely what happens, so there is an indisciplined velocity profile is going to be created. So that type of indisciplined velocity profile को हम क्या बोलते हैं, turbulent flow बोलते हैं. We call it as turbulent flow. So disturbed velocity profile को हम turbulent flow बोलते हैं, indisciplined velocity profile को हम turbulent flow बोलते हैं. So velocities can be predictable. So turbulence can be mentioned like this. So actually speaking, there is no fluid which is permanently laminar, there is no fluid which is permanently turbulent. Okay, so there is no fluid which is permanently laminar or there is no fluid which is permanently turbulent. Every fluid either can be permanently converted from laminar to turbulent or turbulent to laminar. So this is a situation, laminar to turbulent or turbulent to laminar by changing the inner geometry, there is no fluid which is either permanently laminar or permanently turbulent. Every fluid can be convertible from laminar to turbulent or turbulent to laminar by changing the inner geometry of the pipe. Okay, chalo. Now if you see here how it is going to be changed, so this is the inlet zone, so this is the converging zone, this is the throat zone, so this is the diverging zone, and this is the outlet zone. Okay, so these are the different types of zones: inlet zone, converging zone, throat zone, diverging zone, and outlet zone. So here if you see, the fluid here is laminar, and here it is in a process of conversion of laminar to turbulent, and here it has become as turbulent, and here it has become as turbulent to laminar, and then finally it has become laminar here. Finally it has become laminar here. So this is the inlet zone, this is a converging zone, this is the throat zone, this is a diverging zone, this is the outlet zone. So please make a note of these points. Now Reynolds number. What is Reynolds number? Reynolds number is a number by which the fluid characteristics are determined. It is a characteristic function of a fluid. The characteristic function of a fluid by which it can be determined, it can be distinguished whether the liquid is laminar or turbulent. Whether the given liquid is laminar or turbulent. A fluid can be either laminar or turbulent. So if Reynolds number is less than 2000, then that fluid is called laminar. If Reynolds number is between 2000 to 4500, the fluid is in a process of converting from laminar to turbulent. If Reynolds number is greater than 4500, that has become turbulent. If Reynolds number is greater than 10 power 5, that has become highly turbulent. Okay, so these are the characteristics. So please make a note of all these points. Noted? Reynolds number is greater than 10 power 5, it is highly turbulent. Chalo. Now let us move for this. Reynolds number formula, the Reynolds number formula is given by Vd rho by mu. So we can write Q is equal to area into velocity. So Q is equal to area into velocity. So velocity can be determined as Q by A. Velocity can be determined as Q by A. So area can be written as pi d square by 4. So this is Q, this is A. So Q by A, Vd rho by mu na. So A is equal to pi d square by 4. So 4 comes on the top. So 4Q, 1D gets cancelled here. So 1D gets cancelled here. So 1D gets cancelled here. So we are going to get 4Q rho by pi mu d. So where Q is the volumetric flow rate, quantity rate or amount of discharge. So please make a note of all these points. Every slide please make a note of it. Reynolds number का formula 4q rho by pi mu d. Next comes the law of continuity. The next principle is the law of continuity. So what is the law of continuity? Tells that for an incompressible fluid means the density remains constant. So for incompressible fluid, the density remains constant. So try to understand. For incompressible fluid, the density remains constant. The total mass rate remains constant at any 2 points in a closed channel. Okay, so the mass rate is given by the formula mass per time. So mass per time means kg per second. Mass per time is kg per second. So please make a note of these points. Okay, noted. So that is the mass rate. So mass rate is given by the formula mass per time. Mass per time means kg per second. So how much mass per time? So that is the so if you see here, density is equal to mass by volume. So mass rate means how to discuss. So see here, density into volume is equal to mass. So from this, density into volume is equal to mass. So if we divide with per second, this is per second. So volume per second is equal to q. So m per second is equal to m dot. So rho into q, I can write it as m dot. Rho into q, what I can write? What I can write it as m dot. So this particular part I can write as m dot, which is called as mass rate. Okay, so q means area into velocity. So m dot is equal to rho into a into v. So density is equal to kg per meter cube. So this is meter square meter per second. So units are coming as kg per second. So mass rate ka units are important. So ये topic में हमको units and dimensions are very very important. So kg per second. So the total mass rate remains constant. So if you see this diagram, so please note a diagram of this. So in this diagram, it is very clearly mentioned that for any incompressible fluid, the total mass rate remains constant for at any point of time. So if you see at this particular point of time, so this is m1 dot. At this particular point of time, this is m2 dot. So here area is more, so the number of particles occupied will be more, so mass will be more. So when mass is more, velocity will be less. So velocity will be less. So sorry, this is the velocity. So this will be the velocity. So velocity will be less. Next, here area is less, so number of particles occupied will be less, mass is less, velocity will be more. So what I can write, m1 dot is equal to m2 dot. So rho 1 a1 v1 is equal to rho 2 a2 v2. So as the density remains constant, I can write it as a1 v1 is equal to a2 v2. So this is what we call as law of continuity. So v is inversely proportional to area. So please make a note of this point. This is one of the important principle in the fluid dynamics, law of continuity. So what the law of continuity tells, that is very very important. It's not only for your GATE exam, it's also for your university level exams. Not only for your GATE exam, but also for university level exams, and also for interviews also you can use it. Next, so V is inversely proportional to A, area into velocity is equal to constant. Next, Bernoulli's principle. What is the Bernoulli's principle? For an incompressible, rho is constant fluid, the total internal energy remains constant. So what remains constant? The total internal energy remains constant. So what is this total internal energy? See, the total internal energy is equal to the algebraic sum of potential energy, kinetic energy, and pressure energy at those respective points. So mgz plus half mv square. So what I can write here, so this is our volumetric section. So if you see the points here, so this is one point, so this is at one point, so this one point is area is more, the number of particles will be more, mass will be more, so velocity will be less. So we can write this as velocity will be less, the velocity will be less. So this head is more, this height is more, h is more, the pressure is more. Next here, area is less, number of particles will be less, area is less, number of particles will be less, mass will be less, and velocity will be higher, So the lower the height and lower height, pressure will be low. So please try to understand these relations. Fluid dynamics में relation बहुत important है, less height less pressure. Okay, so potential energy के formula mgz based upon its height. So m is equal to kg, g is equal to meter per second square, g meter, so kg meter square per second square. Kinetic energy is equal to half mv square, kg meter square second square. So pressure energy is equal to pressure into volume. So pressure is equal to rho gh, volume is equal to mass by rho gets cancelled. So density, everything. So everything you are going to get kg meter square second square. The units are common everywhere. The units are what always? The units are kg meter square per second square. So now if you see, total internal energy at 1 is equal to total internal energy at 2. So total energy at 1 is equal to potential energy at 1 plus kinetic energy at 1 plus pressure energy 1 is equal to potential energy at 2 plus kinetic energy at 2 plus pressure energy at 2. So potential energy at 1 is equal to, given by the formula m1 gz1, kinetic energy formula half m1 v1 square, pressure energy formula pressure into volume 1. So potential energy 2 formula m2 gz2, kinetic energy formula half mv square. So pressure energy formula pressure into volume 2, Done. m1 gz1 half mv1 square. Density is equal to mass by volume, so volume is equal to mass by rho. So this m2 z2 half m2 v2 square here. So this is a Bernoulli's principle in physics, p2 m2 by rho. So now if I am making no wrong here, so everything is coming like this. So if I divide with time, if I am dividing with the time, suppose this I am dividing with the time second, this I am taking second, this I am dividing with time second, this is with time second, this is with the second, this is with second. So now what happens, this is m1 dot, so this will become as m1 dot mass rate, this is m1 dot, so this is also m1 dot, okay, this is also m2 dot, this is also m2 dot, this is also m2 dot. So m1 dot is equal to m2 dot, so the total mass rate remains constant. Okay, so gz1 half vn square plus p1 by rho is equal to gz2 plus half v2 square plus v2 by rho. So this is the short form of Bernoulli's energy equation. Bernoulli's energy equation. So please make a note of these points. Bernoulli's energy equation. That is a short form. This is a short form. Now, based on this Bernoulli's equation, we're having certain flow meters. So those flow meters are called as mechanical flow meters. Why? Because there is a pressure concept. So this mechanical flow meters is also called as DPTs. DPT stands for differential pressure transmitter. Differential pressure transmitters, DPTX. So because of the differential pressure, the liquid will be traveling from one location to another location. इसके लिए हम DPTs बोलते हैं. Okay, so ये differential pressure transforms can be categorized like this: venturi meter, Orifice meter, nozzle meter, rotameter. This is not rota, so this is a rota. So what we call this as rotameter. This is a rotameter and pitot tube. Okay, so these are the flow meters, rotameter and pitot tube. Okay, so venturi, Orifice, nozzle, rotameter. So इसके लिए differential pressure is the concept. They all will work on the differential pressure. So these are called mechanical flow meters. It's the indirect flow measurement. क्योंकि अगर आपने flow rate measurement करना है, अगर flow rate measurement करना पड़े तो आपको delta P को measure करना पड़ता है. Okay, it's the indirect. So try to understand the indirect. So now let us move for next context of this mechanical flow meters. So different types of flow meters I told you now. So let us go step by step. Different types of flow meters now. Yeah, this was our Bernoulli's equation. So now let us go for the venturimeter diagram. So if you see the venturimeter diagram, so this will be the venturimeter diagram. The venturimeter will be like this. This is the tunnel and there is a divergence like this, and then it is going like this. So now if you see, this is the inlet, this is the outlet. Got it? So now if you see, this is a fluid flow rate. Okay, so I'm taking here 0.1, this is 0.2. Okay, so if you see from the horizontal, this particular height is Z1, this particular height is Z2. So now if I'm taking this, these are the particles. So on this particular height, we check. So this is the area 1 is more, number of particles is more, mass is more, velocity will be less, height is more, pressure is more. But here if you check, area 2 is less, number of particles occupied is less, mass is less, velocity will be more, HT is less, so P2 is less. Okay, so please make a note of the structure. 6 members are watching. May I know who are the 6 members? जो लोग लाइव में है मुझे एक बार थम्स अप दिखाइए बेटा, जितने लोग लाइव में देख रहे हैं मुझे. चलो. Now if you apply the Bernoulli's equation, please check the Bernoulli's equation how you can apply. Note कर दिया? So this is the equation. So complete equation this is. So what I have written? GZ1. So this is a GZ1. So we can write this as GZ1 half V1 square plus P1 by rho, GZ2 half V2 square P2 by rho. So V1 is less here. So you can see the syntax. So here V1 is less, V2 is more, P1 is more, P2 is less. So Z1 minus Z2 if I take off, so G of Z1 minus Z2 if I take off, G Z1 minus Z2, so this is P1 minus P2 by rho, half V2 square minus V1 square. So if I take 2 G Z1 minus Z2, 2 delta V by rho, V2 square minus V1 square. So A1 V1 is equal to A2 V2. Okay. So V1 is equal to A2 by A1 into V2. So if I am writing this V2, I want to convert this V1 also into V2. Why? Because we are interested in the flow rate at the tunnel side. We are interested in the flow rate at the tunnel side. So 2G Z1 minus Z2 I have written. Okay. So 2G Z1 minus Z2 plus 2 delta by rho V2 square minus A2 square V2 square by A1 square. So V2 square if I take common 1 minus A2 square by A1 square. So now if I am writing this 2G Z1 minus Z2 plus 2 delta by rho is equal to V2 square into A1 square minus A2 square divided by A1 square. So if I am taking this particular term to this side, let's just side, A1 square minus A1 square by A1 square minus A2 square 2G Z1 Z2 2W. I am multiplying with A2 square both sides. I am multiplying both sides with A2 square. So this is A1 square A2 square by A1 square minus A2 square 2G Z1 Z2 plus 2 delta by rho. This is Q2 square. So Q2 will be written as, take square gets cancelled, A1 square root of A1 square minus A2 square into A2 square root of 2 delta by rho plus 2G Z1 minus Z2. So this is what we call as a volumetric flow rate. So Q2 can be taken as, what is a Q2? So Q2 can be taken as A1 by square root of A1 square minus A2 square into A2 square root of 2 delta by rho plus 2G Z1 minus Z2. So this one I will take it as velocity approach factor. So what is this M? M can be taken as A1 by square root of A1 square minus A2 square. So that is the M. So this is the A2. So this is the theoretical, but practically if you see, so we have to take the coefficient of discharge CD into Q. CD Q theoretical. So Q2 theoretical I am taking as M A2 square root of 2 delta V rho plus 2G Z1 Z2. So what I can write? Finally, this is a practical expression. So practically this is the expression. Please make a note of these expressions. M is called the velocity approach factor. Everything. CD is the coefficient of discharge. So please consider this and make a note of this. 7 members are watching. जितने लोग लाइव में हैं मुझे एक बार आपका स्टेटस दिखाइए बेटा. You are from, are you from instrumentation? Anybody is from instrumentation? Let me know. If anybody is from instrumentation, let me know. Okay. So please go ahead. yourself. So now this is the formula where m is called velocity approach factor. So this velocity approach factor, I can write it as a1 by square root of a1 square minus a2 square. So where a1 is the area of the inlet, okay, so a2 is the area of the throat. So this is the a2 is the area of the throat. Okay, chalo. Now CD is the coefficient of discharge, that is 0.98. QT is the volumetric flow rate at the throat. Delta P is the differential pressure. So delta P I can write as P1 minus P2 rho G H1 minus rho G H2. So if I take rho G out, H1 minus H2 is coming. Okay, so ultimately what is the CD? CD is called as coefficient of discharge. Coefficient of discharge can be written as CC and CV. Coefficient of contraction and coefficient of velocity. Coefficient of contraction, coefficient of velocity. Coefficient of contraction is, this is A2 by A1. Coefficient of velocity is V2 by V1. Okay, so CD is equal to 0.98 for venturi, 0.78 for nozzle, 0.65 for orifice. Okay, so these are the points. 0.98 for venturi, 0.78 for nozzle, 0.65 for orifice. So coefficient of contraction is A2 by A1 and coefficient of velocity is equal to V2 by V1. So please make a note of these points. So next, Bernoulli's equation. The basic relation of the Bernoulli's relation is the volumetric flow rate that is happening at the tunnel is directly proportional to differential pressure square root. So Q2 is proportional to square root of delta P. So Q2 by Q1. So if I take Q2 dash by Q2 double dash is equal to root over delta P1 by delta P2. So what are the advantages? Coefficient of discharge is 0.98, almost unity. Almost unity. That means losses are less. More efficiency, less drop rate, recovery rate is good. Okay, next, less tendency to get clogged. So suitable for all type of fluids, slurries and practical fluids. Next, best suitable for long distance flows. Venturimeter is lengthy, so it is best suitable for long distance flows. Okay, but the disadvantage of venturi is this: obstructive to the flow, mechanical flow meter, requires compulsory delta P measurement. It is not a direct, so we have to use a manometer. So once you keep the manometer, the mathematical complexity increases. So not suitable for biomedical applications. You cannot insert the venturimeter in the biological applications. Okay, not ease of installation and replacement. Itna easy nahi hai. Chalo. So now these are the formulas. CDMA to square root of 2 delta P rho plus 2G Z1 by Z2. So where rho is the density of the process fluid, rho is the density mass by volume. So density of the water, I think these parameters are useful in calculation. Density of the water 1000 kg, density of the oil 900, density of the mercury 13,600, density of seawater salt rahega, so 1026, so 1.026 kg per meter cube. Okay, 1.026 kg per meter cube. Please make a note of all these points. स्टेप बाय स्टेप नोट कर दो बेटा. देन इसके बाद हम कुछ और एक पैरामीटर्स को डिस्कस करेंगे फटाफट. Have you noted these values? Yeah. So these are the density values which will be useful for your numerical problems. Numerical problems. 8 members watching. Okay. Chalo. Now let us see one more. Specific gravity. What is the definition of specific gravity? How we can define the specific gravity? Specific gravity is defined as when you are expressing density of the fluid with respect to density of the water. That is what we call as relative density, or we can also call as specific gravity. You can call it as specific gravity or relative density. Okay, specific gravity of water is equal to 1. Specific gravity of oil is 0.9. Specific gravity of mercury is 13.6. Specific gravity of seawater, that is 1.026. Specific gravity of air 0.001026. 0.001026. So 1000 by 1000, 900 by 1000, 13,600 by 1000, 1026 by 1000, 1 by 1000. Okay, so that is what we call as specific gravity. Specific gravity does not have any units. It is also called as relative density. What we call it as relative density. So now specific weight. What is specific weight? The specific weight is defined as rho into g. Rho is the density. Density is equal to mass by volume, kg per meter cube. So meter per second square. So specific weight is rho g. So that units are coming kg per meter square second square. So specific weight of the water is 980. Specific weight of mercury is 13,380. Specific weight of oil is 8,820. Okay, chalo. Now next comes the Orifice meter. So please note on this diagram of Orifice meter. Okay. Yes, Saranash. Merry Christmas. Merry Christmas. Thank you. Thank you very much. Yeah, this is Orifice meter. If you see the Orifice meter structure, inside there is a circle and after that there is small area. So here area of the inlet is more. Here area of the orifice is less. Area of this particular region called vena contracta is still least. Okay, so it is a zone at which area becomes least and velocity becomes maximum. It is the area at which it becomes least and velocity becomes maximum. So this is what we call as inlet area, this is orifice area, this is the vena contracta area. It is a zone at which area becomes least and velocity becomes maximum. Okay, so Q orifice is equal to CDMA to square root of 2 delta B by rho plus 2G Z1 by Z2. So orifice ka coefficient of discharge will be equal to 0.65. 0.65. So what are the advantages? The advantages are smaller size, so ease of installation and replacement, best suitable for short length fluids. Best suitable for short length fluids. Are you from instrumentation? Okay. Best suitable for short length fluids. Chala. Next, the most important thing, disadvantages. The disadvantages are also very high. So coefficient of discharge is 0.65 now, it is very least. So more losses, so poor efficiency, drop rate is more, poor recovery rate. Okay. Next, more tendency to get clogged, not suitable for slurries and particle fluids. So why? Because as the intersection part is there, so this is what we call as particle fluids. Note down. And it is a mechanical flow meter, output is not electrical, obstructive to the flow, indirect flow measurement. Why? Because we are not measuring the direct flow. Okay. For delta P measurement, U-type manometer is required. Again, a mathematical complexity and design complexity is increasing. So these all are the disadvantages. ओके भाई गेट 2026 का कौन हा ओके so if you see this compulsory you need a manometer chalo let us go for the next nozzle so this is a nozzle the nozzle is very interesting it is not like orifice it is not like venturi so there is no divergence zone here so this is the nozzle shape of the nozzle will be like this so this is the shape of the nozzle so the q is given as CDMA2 square root of 2 delta below 2 Z1 minus Z2. So this is Z1 minus Z2. Formula is same for all. This formula is same for all. Okay. So CD is taken here 0.78. Okay. So now please answer this question. Please try to answer this question. Make it fast. Try to answer this question. इसका आंसर क्या है? The differential pressure transfer of flow meter using venturi tube reads 2.5 10 power 5 Pascal for a flow rate of 0.5 meter cube per second. So when Q1 is 0.5 meter cube per second, then the differential pressure is 2.5 into 10 power 5 Pascals. Next, for a differential pressure of 0.9 into 10 power 5 Pascals, what is the flow rate? So Q1 by Q2 is equal to square root of delta P1 by delta P2. So delta P1 is 2.5 into 10 power 5 divided by 0.9 into 10 power 5. So Q1 is equal to 0.5, Q2 is equal to this. So this gets cancelled. 25 by 9, so that will become as 5 by 3. So Q2 is equal to 0.5 into 3, 1.5 by 3. So Q2 will come as how much? 0.3. So the right answer for this question here is 0.30. Anybody has done this question? Okay, sure. Let us go for the next question. These are different types of questions. So please answer this question. When a contractor is a cross section where the flow rate is minimum, for a restriction type flow meter, for orifice meter, if D is the diameter of the orifice opening, then the area of the Venn contractor is approximately dash. So always remember, area of the Venn contractor will be lesser than area of the orifice, and that will be lesser than area of the inlet. So that is 0.6. The coefficient of discharge will be in the range of 0.65. So area at the Venn contractor is least, and the velocity at the Venn contractor will be higher. So that is approximately 0.6. So please note down 0.6 A pi d square by 4. Orifice opening से कंपेयर करें तो लेस हो जाएगा 0.6 pi d square by 4 होगा. Okay, चलो. Answer this question. Theoretical questions are very important with respect to flow chapter. Yes. Which of the following flow meters has the lowest pressure drop? Lowest pressure drop, delta P is least, means recovery rate is good. Recovery rate is good. Recovery rate is good for venturi meter. So the right answer is venturi meter. Okay. So that's it. These are the important topics. Enough for today. So जो हमने डिस्कस किया था ये कॉन्सेप्ट अब डिस्कस करके जाएंगे. ओके. सो प्रीवियस लेक्चर्स में हमने टेम्परेचर डिस्कस किया था. इसके पहले हमने आरएलसी ट्रांसड्यूसर्स डिस्कस किया था. आज का क्लास में हमने फ्लो चैप्टर डिस्कस किया था. लॉ ऑफ कंटिन्यूटी, Bernoulli's equation, mechanical flow meters, and gate PYQs का just introduction discuss किया था. Okay, so please have the slides as a reference. ये slides आपके reference के लिए अच्छा use होगा. So miss मत करना ये slides को. Okay. Enough for today. Thank you.